Welcome to the next lecture of electromagnetism. Today we're going to begin with a lecture on image charges. What are image charges? Well, they're the next chapter of conductors. So recall that a conductor is the following. Suppose you have a metal spherical shell. Well, if you have any charges, if you place any charges, all of the charges will migrate to the surface of this metal. Why is that? Well, metal is a conductor, and conductors have zero electric fields inside of them, and thus they have a volume charge density of 0. So the main thing you should remember about conductors, first and foremost, they have an electric field of 0 within their radii, within R less than capital R, where capital R is the radius of the conductor, and conductors are equipotential, which means that the potential across their surface is equal. Otherwise, if the potential wasn't equal, then there would be some kind of a net electric field, right? So those are the two main ideas about conductors that we have to remember. And now we move on to proposing a simple problem. What if you had a conductor that was a plane? So you have a planar conductor, and it is an infinite planar conductor, so it stretches out in all directions so that you may neglect end effects. So it is an infinite planar conductor. But one more thing, I'm going to ground this conductor. What does that mean? Well, that means it's going to be held at an electric potential of 0. So this is an infinite planar grounded conductor. Now, what would happen if I brought a charge of magnitude q near the surface of this conductor? Well, let's first think about this analogous situation. What would happen if you brought a charge q near the surface of this spherical conductor? Well, we know that the spherical conductor cannot have any electric field within itself. So what it's going to do is, let's say that this is a positive charge q, it's going to protrude out electric field lines as follows. But of course, those electric field lines will enter into the conductor unless the conductor reacts. And in fact, that's what it's going to do. The conductor will bring in some negative charges near the part of the surface where the positive charge is, so that the field lines for the positive charge ends right at the surface of the conductor. So the conductor is preventing this positive charge from disturbing its 0 electric fields inside. Much the same way, and we found that this would introduce a disturbance onto the surface of this spherical shell. That's what we were just saying, right? The spherical conductor is going to respond to this charge q by introducing some negative charge here, by moving some of the negative charge from the other side onto this side. Now here, when I bring a charge q near the surface of this infinite planar grounded conductor, it's also going to respond, just like a mirror, right? It's going to induce some kind of a negative surface charge. So there's going to be some induced negative surface charge, this positive charge, so that the field lines end right at the surface of the conductor, and so that the electric field is 0 within. Now, the question is simple. What is the electric potential of this charge distribution above the plane? So here's the question. What is the electric potential, V, electric potential, V, above the plane? Well, how can we answer that question? We don't know how much charge is induced on the surface of this conductor. It doesn't seem like this is an infinite plane, so maybe we could construct some kind of a Gaussian surface and deduce the electric potential from there, but we don't know if that's going to work. So what else can we do? Well, here's where Poisson's equation comes in. This is the physical statement of our problem. So let me write that down. This is the physical statement of our problem. Translating this physical statement into a mathematical statement means using Poisson's equation, right? Poisson tells us that nabla squared of the electric potential is the volume charge density over epsilon naught. If you're wondering where this comes from, this is simply just another way to write the Maxwell's equation, that the divergence of the electric fields is the volume charge density over epsilon naught. The curl of the electric field is 0, thus admitting a scalar potential where minus the gradient of the scalar potential gives rise to the electric field. And so if we plug in this minus gradient of the electric potential back into the divergence of my electric field, that gives me the divergence of minus the gradient of the electric potential is the volume charge density over epsilon naught. And just simplifying via the rules of vector calculus gives us nabla squared, the electric potential is minus rho over epsilon naught. There should be a minus sign over here. So this is Poisson's equation, which holds for non-zero volume charge densities, whereas Laplace's equation only holds for charge densities where rho is 0, right? So Poisson is only for cases where you have a non-zero volume charge density, which is what we have here, right? Because of the charge Q and also because of the induced negative surface charge. So how can we figure out what the electric potential is? Well, I mean, sure, the Poisson's equation includes the electric potential in its statement, but how can we extract it out of there? Well, here's one more thing. We have the following boundary conditions where the following boundary conditions apply. First of all, let's construct some kind of a coordinate frame here. So I'm going to say that this is my x-axis pointing out of the board, my y-axis going to the right, and my z-axis headed upwards. Okay, so here's my arbitrary coordinate reference frame, and now I'm going to say the boundary conditions are as follows. As I get far away from this charge distribution, in other words, when when r is much greater than this separation between the charge and the plane, let's call that separation A. So when r is much greater than A, then the electric potential should approach 0. The electric potential should approach 0. In other words, if I'm using Cartesian coordinates, when x squared plus y squared plus z squared is much greater than A, then we should have 0 electric potential, or close to that. And secondly, because this infinite planar conductor is grounded, we expect that when z equals 0, the electric potential should equal 0. Not approximately 0, just equal to 0. So these are the boundary conditions for this problem. So we have Poisson's equation satisfying these boundary conditions. How can we extract V? Well, this is where one of the most powerful tools in Poisson's equation and Laplace's equation comes in, which is the uniqueness theorem. The uniqueness theorem. Uniqueness theorem. The uniqueness theorem says this. You have a very hard problem with certain boundary conditions and you don't know how to find the electric potential, right? If you can find an analogous problem where the electric potential is much easier to find, but that analogous problem satisfies the same boundary conditions, then the electric potential in your analogous problem will be the exact same as the electric potential in your original problem. Let me say that again, but let me draw a picture on the board. The uniqueness theorem says the following. If you have a difficult problem so you have Poisson's equation, nabla squared V is minus rho over epsilon naught, Poisson's equation, okay. So you have a difficult problem with certain boundary conditions and you're trying to extract the electric potential for this problem. Okay, so you don't know how to figure out the electric potential. Uniqueness theorem says that if you can find an analogous problem where the boundary conditions are the same, but the electric potential is much easier to find, then the potential for this new analogous problem will be the exact same as the potential for the original problem. You are guaranteed that via the uniqueness theorem. So, how does that help us? How can we leverage that to help us find the electric potential for a charge near a conducting plane? Well, here's how. So, we have our x, y, z axes, x, y, z. Once again, we have a charge q, but this time we don't have any infinite conducting grounded plane on the xy plane. Okay, so we don't have anything on the xy plane, no grounded conductor. But we have, let's say this distance here is a, as was previously, but below the xy axis we have the following: another charge, which we know that the induced surface charge has to be negative so as to counteract the electric field lines from the positive charge, so that there is zero electric field below the conductor. And so because of that, we expect some kind of a negative charge. So just for symmetry reasons, let me say this is negative q. Okay, so this is negative q. And so what is the electric potential for this distribution? Well, this is pretty simple, right? This is 2 point charges. The electric potential is going to be 1 over 4 pi epsilon naught. The first one, I'm going to color code it, the blue charge, q, over x squared plus y squared plus z minus a squared, because it's going to be closer if we have some kind of a, if we want to find the electric potential somewhere in the first quadrant, for instance, all raised to the 1/2 power, plus the electric potential due to the negative charge, which is going to be minus q over x squared plus y squared plus z plus a squared, all raised to the 1/2, since it's going to be farther away from wherever we want to find the electric potential. And so this is our electric potential for this problem, right? And what do you notice? Well, does it satisfy the same boundary conditions we had for our original problem? Let's see. Does the electric potential approach zero when r approaches infinity? In other words, when we get farther and farther away from the origin. So does the electric potential approach zero when the radius approaches infinity? Well, let's check. As the denominator increases, of course, the total electric potential is going to decrease. Eventually, it's going to approach zero. So first boundary condition, yes, sir, check. This new analogous problem satisfies the first boundary condition. Let's check the second one. Does the electric potential equal zero when, does the electric potential equal zero when z equals zero? Well, let's check. When z equals zero, this is 0, this is 0, so the denominators are the same, but this one is negative, the first electric potential, hence they cancel out. So yes, as a matter of fact, the second boundary condition is also satisfied. And so, since both of our boundary conditions are satisfied for this analogous problem, that means the electric potential for this analogous problem is the same as the electric potential for original problem. Well, what does that mean? Well, we've just found the potential for our original problem. We've answered our question, which was, what is the potential for this charge distribution when you bring a charge of magnitude q near an infinite planar grounded conductor? So this was the big idea of the lecture, that infinite planar grounded conductors behave almost like mirrors, in that they take this charge q and they flip it over. Not only in sign, not only does this plus q become analogous to a minus q charge, but that minus q charge is situated a units below the original, or below the origin. So this original problem is exactly analogous to this new problem. So that's what we'll be considering from now on when we're faced with these kinds of image charge problems. Let's take a look at our first image charge problem. Here is another view of problem 1. Let's check out problem 1. Here's the first problem. 2 point charges are placed on the z-axis above an infinite grounded conducting plane. The charge 2q is placed at z equals 2a and minus q at z equals 4a. So 2a, 2a, 4a. First part asks us to find the electric potential at a general field point xyz. Okay, so let's start with the first problem. Well, we saw that the electric potential for this charge distribution, a collection of point charges above an infinite grounded conducting plane, is exactly analogous, via the uniqueness theorem, exactly analogous to the following problem. to these 2 point charges being reflected below the xy plane, so that you have minus 2q, a distance of 2a below the origin, and plus q, a distance of 4a below the origin and 2a underneath its neighbor. So this is the analogous problem for finding the electric potential for part A. So that's why they call it an image charge, because you see an image, a reflected image of the original charges under this plane. That's the whole idea behind the name. So now how can we find the electrostatic potential? Well, now it's quite easy, right? Now it's going to be V is 1 over 4 pi epsilon naught. Just add up the electric potentials for each point charge. For this guy, minus q, we're going to have minus q over x squared plus y squared. And notice that this one is 4a above. So it's going to be z minus 4a, because it's going to be closer to wherever we want to find the electric potential. For 2q, it's going to be likewise, except now it's going to be x squared plus y squared plus z minus 2a instead of 4a to the 1/2 power. And now we're going to add in the electric potential due to the image charges. So plus the electric potential first to this one, I wrote 2g, minus 2g. Instead, it should be minus 2q. Let's make that minus sign obvious. So minus 2q, notice how that this and this are oppositely charged. Their image is oppositely charged the original. So you're going to have x squared plus y squared plus z plus 2a this time, because it's farther. And finally, for the last image charge, you're going to have plus q. So plus q over x squared plus y squared plus z plus 4a squared, all to the 1/2. Okay, and so this is the electric potential for this entire charge distribution. Not too bad, not too bad. And then now we have to find the surface charge density induced on the conductor at z equals 0. In other words, we have to find the surface charge density induced on this infinite plane. Well, how can we do that? Well, now that we found the potential, here's what we can do. Recall that the partial derivative of the outer potential minus the partial derivative of the inner potential evaluated at the surface, which in this case is z equals 0. Sometimes you'll have r equals capital R for spheres. This is equal to minus the surface charge density over epsilon naught. So we can just leverage this to figure out the surface charge density for this charge distribution. So, well, what we have to do in this case is, sigma is going to be minus epsilon naught partial v partial r. Okay, well, in this case, the normal vector is not going to be the radial vector, it's going to be z hat or k hat. So we'll have to partial differentiate this entire electric potential term, all 4 of these terms, with respect to z, and then negate it and multiply it by epsilon naught to get the surface charge density. So let's do that. I'm going to erase this image, and we're going to go ahead and calculate the surface charge density. So let's take the partial derivative of this with respect to z. So partial z of this entire thing is going to give us what? Well, let's first start with this one. So I'm going to have, let's write it as a minus exponential. So minus q x squared plus y squared plus z minus 4a squared to the negative 1/2 power, right? So if I take the derivative of this, this negative 1/2 is going to come out. I'm still going to have my minus q, all the stuff inside. Now take away 1 from the exponent, giving us minus 3/2, and then differentiate the inside with respect to z via the chain rule, so that this gives us 2 times z minus 4a. Okay, so we're just going to follow that same strategy, repeat it 4 times for each of the 4 terms, and add it up. So let's do that. Partial v, partial z. Hopefully you can see down here. I'm writing here because all the space is taken up by this behemoth. Is 1 over 4 pi epsilon naught. Minus q is going to stay minus q, but as I said, minus 1/2 is going to pop out. Okay, we're going to have all that stuff inside. X squared plus y squared plus z minus 4a squared to the 1/2 is what it used to be, but now it's going to be 3 halves on the denominator, so it's going to be negative. So minus 3 halves. Okay, and now because of the chain rule, we have to differentiate the inside, giving us a nice 2 times z minus 4a. Okay, so that's the differential, that's the derivative of the first term. Now rinse and repeat 4 more times. So plus, again, you're going to have a factor of minus half coming out from the exponent. You're going to have this 2q. You're going to have this entire term, x squared plus y squared plus z minus 2a squared to the negative 3 halves. And then, because of the chain rule, we differentiate the inside to get 2 times z minus 2a. So that is the derivative of the second term. Now let's do the third term. So this is going to give us minus 2q times, oh, I forgot my factor of negative 1/2. Okay, I have it there. So negative 1/2 times negative 2q times all of this, x squared plus y squared plus z plus 2a squared, okay, to the negative 3 halves times 2 times z plus 2a. Now let's do the second one. We're going to have negative 1/2 once again coming out from the exponent times q times x squared plus y squared plus z plus 4a to the negative 3 halves, all times 2 times, I don't need that parentheses, 2 times z plus 4a. And there you go, that's the differential. So all of this needs to be simplified, but that is the general idea for this problem. And in fact, one more thing, since we're evaluating this as a surface charge density at z equals 0, we have to make all of the z 0. So this z becomes 0, this z becomes 0, that becomes 0. So let's actually erase all the z's because they're going to become 0 at the surface. So we're left over with this. So z minus 2a just becomes minus 2a. Okay, this just becomes 4a. This becomes minus 2a. That becomes plus 4a. So what are we left with? Minus minus is going to give us plus here. So might as well not write that. And what other simplifications can we make? Minus minus gives us plus. Any other minus minus pairs? We have this a minus and that's a minus. So that's going to give us a plus. And this stays a minus because there's no canceling minus on the other term. Minus 8a, but you have half over here, so that's going to give us minus 4a. So to have 4a, and well, this half and 2 is going to cancel out. So these two cancel out, aq, but these won't cancel out because one has 16a squared, one has 4a squared in the inside of the parentheses. Going out this half and 2, and so that's going to give us 4aq right here, 4aq. And finally, for this term, I'm going to have minus half times 8. So that's going to give us minus 4aq. 4a squared is associated with plus 4aq. So what we're going to have in the end is partial v partial z is equal to 1 over 4 pi epsilon naught times minus 8aq after we added up the like terms, associated with 16a squared, okay, and plus 8aq associated with 4a squared. So x squared plus. So I've written it down right here. And now if we negate this entire thing and multiply it by epsilon naught, we'll get the surface charge density. So negate all of this, negate it, multiply it by epsilon naught. Hopefully you can see that minus sign. Multiplied by epsilon naught. And now we have our surface charge density. This is the surface charge density. The final part of this problem asks us to find how much energy is stored in the arrangement. Well, all we have to do is find the pairwise potentials. So let's first consider these two. What's the pairwise potential for those two? Well, Q times the potential due to 2Q. So, and it's worth noting that these distances are 2a each. So this is 2a, this is 2a, this is 2a. So we're going to have minus q times 2q over 2a. That's for the first one. And of course, there's going to be a factor of 1 over 4 pi epsilon naught outside everything. Okay, plus, let's consider now minus q and minus 2q. So minus q times minus 2q. How far apart are they? They're 6a apart. Okay, and likewise, I just repeat on for all the pairs, which turns out to be 6 pairs. So let me just write out a couple more. Maybe I'll do all of them. Let's do minus q and plus q now. That's going to be minus q times plus q. How far apart are they? Well, as far apart as can be, which is 8a. Now let's consider these two. 2q and minus 2q. So let me write them here. 2q and minus 2q. And how far apart are they? They are 4a, 2a, 6a apart. And now let's consider these two. 2q and plus q. So 2q and plus q. Let's check to see we haven't done it before. We have not. And how far apart are they? 2q and plus q is 6a apart. And the final one we have to consider, we've considered these two, these two, these two, these two, these two. Final pair is minus 2q and plus q. Minus 2q and plus q, which are 2a apart. And this is the energy, electrostatic energy for this charge arrangement. Let's check to see there are 6 terms, as should be, because if you do 4 choose 2, that works out to be 4 factorial over 2 factorial 2 factorial, which is 6. So we should have 6 terms, 1, 2, 3, 4, 5, 6. And indeed that is the case. So that's how you solve problem 1. Let's take a look at the next one. Here is the problem. Let's check out problem 2. Here's our problem. A uniformly charged disk of radius capital R has a charge per unit area sigma and is a distance a above a conducting plane to which it is parallel. Find the electrostatic potential along the z-axis in the region above the grounded conducting plane. Okay, so to solve this problem, first things first, let me grab the right marker. We have to figure out the electric potential for a charged disk. Well, I don't know about you, but I totally forgot what that is. So we'll have to derive it on the spot. So consider this charged disk. How can we figure out its electric potential on the z-axis? On the z-axis. Well, consider this. The electric potential for a point charge is nothing more than 1 over 4 pi epsilon naught q over r, right? kq over r. The electric potential for a point charge. Well, in this case, we have a surface charge density, sigma. So that q would be replaced by sigma dA, or sigma A if you want the total charge, sigma dA if you want a differential amount of charge dq. But what is dA for a circle? Well, dA for a circle, if you recall, is nothing more than r d theta dr. Let's put prime down all of these because we'll be integrating them across. This should be phi because it's the angle on the axis, xy plane. So that is the differential area for a circle. We've separated q into sigma dA. Is there anything else we've got left to do? Well, yes, this r. What should r be? Well, r should be rb. Anyway, that's a joke for the Arby's fans out there. But r should be simply x squared plus y squared plus z minus wherever we are. But we are trying to find the potential along the z-axis. So there is no x or y to consider, right? So keeping life easy. So where do we want to find the electric potential? Along the z-axis. So z times k hat. Minus, where is it coming from? It's coming from this circle. So r prime cosine phi prime I hat plus r prime sine phi prime j hat, sine phi prime j hat, plus a k hat, where a is where this whole disk is located. So that means r is going to be nothing more than this magnitude, the magnitude of this vector. So let's write out our electric potential for a charged disk. It's going to be V equals double integral. Phi is going to go from 0 to 2 pi as usual. R is going to go from 0 to capital R. We're going to have 1 over 4 pi epsilon naught, our constant. Q is going to become sigma. dA is going to become R prime, d phi prime, dr prime. And R is going to be the magnitude of this vector, which is, well, if you find the magnitude of this, these R primes are simply going to become R prime squared plus Z minus A squared, all to the 1/2 power. Now, this R prime squared came from squaring these two I hat and j hat components and adding them together. As you very well should know by now, cosine squared plus sine squared is 1, so hence we're left with just R prime squared. So now let's go ahead and integrate this. The phi integral is pretty easy. It's just going to be 2 pi, and so we can do that integral for the phi and pull out all of our constants. So that'll make life at least a little bit easier for us. So we'll have v is equal to 2 pi sigma over 4 pi epsilon naught. So far, I pulled out all the constants, integrated phi. Now comes the real business, which is the integral from 0 to r of r prime dr prime over r prime squared plus z minus a squared to the 1/2 power. So now if you remember calculus, then you'll recall that at this point we can make a u substitution where u is equal to r prime squared plus z minus a squared, giving us that du is simply 2r prime dr prime. And so we may write this as, let me first tackle this integral. This integral may now be written as the integral of r prime over u to the 1/2, right? Since all of this is now u, and dr becomes replaced with du over 2 prime, du over 2r prime. Notice that r primes cancel out, which was the whole point of the u substitution, leaving us with 1/2 of the integral of u to the negative half du. Well, what is the integral of u to the negative half du? It's u to the half over half. So these two cancel out, since 1 over half is just 2, which cancels out with the half. And so we're left with the integral being u to the half. And so we can now say what our original electric potential was. It is, canceling out the pi's, canceling out and simplifying, we have sigma over 2 epsilon naught times u to the half, and u recall was this, so u to the half r prime squared plus z minus a squared, this to the 1/2 power, as r prime goes from 0 to r, capital R. So the potential for this charged disk is going to be sigma over 2 epsilon naught times, plug in capital R, so you're going to get square root of r squared plus z minus a squared. And if you plug in 0 here, well, you'll be left with nothing but this square to the half, which is just minus z minus a. So this is the electric potential for this guy, but remember, this is analogous, since this is above an infinite conducting grounded plane, this is analogous to the situation in which you have this charge disk, but also an image of this charge disk under the xy plane with a charge density of negative sigma. Okay, so, and since this is under the xy plane, it's going to be under by the same amount due to symmetry by a. So just plug in negative a here and we'll get what we should deserve. So we'll get plus the charge density due to the negative one, which is going to be square root of, now it's going to be minus a, which is just going to be plus a. So r squared plus z plus a squared. And now we're going to also subtract from this z plus a, because of that image charge disk being a below the origin. So this is the answer for this problem. Is there any other part? No. So that's it for this problem. Let's check out the last one. Here is the problem. Let's check out the last problem. Here's our problem. two grounded conducting planes meet at a right angle and a point charge Q is placed at an XYZ coordinate of A, B, D. Give the electrostatic potential in the region between the plates. So here's how we can solve this problem. This point charge Q may be imagined as being placed here at an X coordinate of A and a Y coordinate of B. And a Z coordinate of D, which is not shown here because the problem is symmetrical around Z, hence Z is relevant. So Q would first be reflected by this conducting surface, this conducting plane, because there are two, not one, but two grounded conducting planes, one on the X, one on the Y axis. So this charge would first be reflected by the conducting plane on the X axis, producing minus Q here. Now this is not really what actually happens. This is just the analogous problem, which via the uniqueness theorem for Poisson's equation produces the exact same electrostatic potential as the original problem here. So the analogous problem says that this original charge Q would be reflected first along the x-axis and then along the y-axis, along the other conductor, producing minus Q here as well. And then finally, due to symmetry, there would be another positive charge Q over here. So you can see the symmetry Q minus Q, Q minus Q minus Q, Q. So you can argue by symmetry that this is indeed the analogous problem. So now all we have to do is, well, this is minus A and this is minus B. All we have to do is find the electrostatic potential for this simple point charge distribution. And what is that? Well, V is equal to 1 over 4 pi epsilon naught. Let's do the positive charges first, so that we'll have Q over x squared plus, well, actually not x squared. For this first positive charge, we'll have x minus a squared plus y minus b squared plus z minus d squared, all to the 1/2. For the second positive charge, which is located at minus a minus b, we shall have Q over x plus a squared plus y plus b squared, since it's farther away, plus z minus d squared, all to the 1/2 power. So we found the electric potential due to these two positive charges. And now for the blue charge, which is minus Q, we have x is going to be plus, but y stays minus. So x plus a squared plus y minus b squared plus z minus d squared, all to the 1/2 power. And finally, the electrostatic potential for the minus Q charge in the fourth quadrant is going to be, this time x will stay positive, x will stay negative, y will become positive. So that you have x minus a squared, y plus b squared, plus z minus d squared, all to the 1/2 power, because we're finding electrostatic potential, which has 1/2 instead of 3/2, unlike the electric fields. So folks, this is the answer for this problem, and hopefully you learned something. We'll see you in the next one.